So I will start with the first presentation about the laboratory testing of the durability of airtightness, review the state-of-the-art of existing studies. So this state-of-the-art has been done in the context of the durability project. It was the first task of the durability project doing this state-of-the-art. And so the objective was to learn from previous studies that has already been done in Europe and the rest of the world to improve the protocol for the other tasks of the durability project. So the second task was the field measurement. It has been presented during the previous webinar last month, and so there were the state-of-the-art for field measurements. And the third task of the durability project was laboratory testing that Andres will be presenting just after me. And so the state-of-the-art was aiming at, trying to help to elaborate the protocol for laboratory testing. So here I will present the part dedicated of the state-of-the-art dedicated to laboratory testing. So the first part was on loads on the air barrier, because to develop a laboratory test, we have first to find out what are the loads that the samples shall endure, the loads that to be endured on the sample, and then the experience on other laboratory testing. So, first of all, the loads on the air barrier. We have just started with the pressure loads sustained by the air barrier, and that was quite the heavy part of this subject, because, well, we have everything we need in the literature to find out what is the pressure load sustained by the air barrier. We can find easily what is the maximum wind speed in a country. For example, in France, it's 60 meters per second, and when you only look at inhabited area, it's 41 meters per second at meteorological stations. So then you have to translate this wind speed at meteorological station in a wind speed at building level. So there is a standard for that, and ISO standard doing that very well. Then when you have this wind speed, you can translate it in wind pressure with a CP coefficient. Also, we find CP coefficient easily in the literature. So you've got the maximum pressure sustained by the air barrier. And then in the literature also you have a publication from Ackermann that says that around 60 to 75% of this pressure made by wind is sustained by the air barrier. So you have the maximum that can endure the air barrier. And then if you look at British standards, you have wind cycles that are made to be equivalent to 10 years. So if you do it 5 times, you have 50 years, of course. So according to the maximum pressure you have calculated, you do cycle of, 960 cycle of 40% the maximum, and 60 cycle of 60% the maximum, etc., to get the equivalent of what her air barrier will sustain during 10 years. So this was the heaviest part. Now, and then we have looked at what was the temperature and humidity load on the air barrier. Well, first of all, it depends on the air barrier position. Of course, it is not the same thing if the air barrier is inside the insulation, like plasterboards or health, or outside the insulation, like plasters on masonry, or some membranes that can be located outside the insulation. And of course, they do not have to sustain the same load. So it should be maybe different protocol for the two of them. Then we have tried to look at artificial aging due to temperature variation, and there is, some rules that we call time and temperature superposition principle. The principle is that when you maintain a polymer at a high temperature, which remains below its glass transition temperature, and you use Arrhenius law or WLF model, then you can have an equivalent to time aging. But the problem is, all those laws depend on the material you have, and if you are trying to apply them to an assembly of material, like a membrane and an adhesive, or a plastic board and a mastic, then you cannot, there is just not one equivalent law, so how you can apply this law remain a question. And also it's important to keep in mind that heat treatment is not enough to make an hygiene protocol, because you have physical, mechanical, and chemical hygiene of products, and you cannot only with temperature variation say that this is an hygiene protocol. Also, when you look at those hygiene protocol in stove, we find out inconsistency in literature. For example, if you remain 21 days at 65 degrees and 80%, according to ASTM, it will be equivalent to 10 years, but according to SATAS, it will be equivalent to 3 years of aging, which is not exactly the same. So after this literature review, for us, it seemed impossible to ensure an equivalence between natural and artificial aging in the context of airtightness assembly. So we can just age the products, but we cannot say, okay, it's equivalent to 50 years of aging or something like that. Now let's have a look at the laboratory testing that has already been done to test the durability of projects. So in the context of the durability project, we have found 6 studies that were performed before 2016, year where we have done this review. And also I have included here the test we have in France on adhesives. So we have those 6 studies. It's interesting to see that the approach were all very different from one study to another. In some studies, they are testing just a small assembly of 2 or 3 products, like here, here, and here. And in some other studies, they have reproduced a full wall construction. So like in Belgium and Switzerland here, you have a full wall with a structure. So here it's masonry, here it's a wood structure, insulation, and the air barrier. And well, the hygiene protocol was very different from one test to another. Here it was just water pressure test, here water pressure pulse test, and here they have maintained at 93 degrees and 84 Pascal. That was for ductwork airtightness products. Here they have maintained at 80 degrees and done cycle of humidity. Here they have done cycle of temperature and cycle of frozen and rain and UV also, because it was made to be outside. Well, it was a rain screen, so it can be submitted to UV also. In Belgium and Sweden, they have done pressure cycle. You see that in Belgium it reached 1000 Pascal, which is quite a huge storm, while in Sweden they remain between minus 150 Pascal and plus 150 Pascal. Then humidity cycle and temperature cycle, one after the other in Sweden, in Belgium, and in Sweden temperature and humidity was maintained together. Also, the analysis of the result was very different from one study to another. Well, in most cases they were testing the airtightness of the assembly after the hygiene protocol. With the adhesive standard in France, we test the longitudinal and the transverse shear of the adhesive only, and not the airtightness of the assembly. And what is interesting also is that there were huge difference between the duration of the test, from 45 minutes here with the pulse water up to 2 years in the protocol in US. And eventually, what is interesting also is that very few studies say that this protocol is equivalent to a certain amount of year. Most of the time, it's just a protocol giving a resistance in terms of durability, but they do not pretend to be equivalent to 30 or 10 years. Other important results we have seen in those studies, first of all, was in the Swedish study. We see here that Sweden has done its study in 2 parts, in fact, and in the first part of the study, they have tested the airtightness of the cells and also the aging of the products themselves, of the adhesive, in terms of peeling and tearing. And they find out that there is no correlation between the aging of the product alone and the durability of the assembly. it was due to compatibility problem between film and tapes, and it's because there were some air channel appearing between the membrane and the tapes, while the tape was still very sticky, so no problem of peeling and chewing, but there is those air channel appearing that making the assembly no longer airtight. So it has been necessary, so they conclude that it was necessary to develop a durability test on a complete airtightness system and on a full-scale setup. So that's why they have done these 3 meter per 3 meter walls for the follow-up of the study. And they also tested the impact of implementation in cold and dusty environment, and they found out that there was a big impact of the temperature and the dusty environment when the air barrier is implemented. So, conclusion of those laboratory testing, we see that, of course, the results vary from one study to another, mostly because there is no standardized protocol, so it's very difficult to compare one study from another. But as a general conclusion, we observe that results observed on product alone are not always consistent with a gene observed when they are implemented, and also the durability of the air tightness really, and not only the durability of the product. Products results with standard tests, so peeling, etc., do not correspond to their air tightness ability, and this is very important. We have seen also that there may be a big impact of the implementation and the environment of during the implementations. We also have seen that the products do not react the same way in extreme conditions and in usual conditions, so it's very important not to test the product under too extreme conditions, because it may not be, well, what will happen in true life. And, well, a standard is missing to characterize products and, above all, assemblies in terms of air tightness. And also what we have noted is that none of those laboratory tests have tested the reproducibility of their methods. And this is a major limitation from scale 1 system, because it's very expensive to implement, and therefore, and the impact of implementation is very huge. The bigger it is, the impact of the implementation is. And so it is difficult to do reproducibility tests on those systems. So the steps to define a protocol is first to design a testing facility that, while considering that if you are too reduced scales, it may not be representative, but if it's too big, then it's not repeatable and reproducible. So you have to find the good site for that. You have to define clearly the implementation condition of the air barrier, temperature, relative humidity, dusty area, etc. You have to specify the loads on clear basis, and considering that worse conditions the air barrier undergoes in the field, and makes preliminary tests to evaluate the impact of whether the worse is a steady state or is it the cycling that prevails. You have to focus on the comparison of products and not try to do an actual aging and saying that, yeah, it will last 50 years or something. And it's also important to implement small-scale preliminary tests to evaluate the feasibility and the results before making full-scale tests. So, as a conclusion, I would say that, yeah, a standardized protocol is really missing for testing the assemblies of airtightness assemblies. So it's important to find a good balance between two reduced tests that do not characterize the airtightness and too complex that are not reproducible. Regarding the loads that the air barriers undergoes, pressure loads are quite easy to define, but when it comes to temperature and humidity loads, it's much more difficult to define the protocol with this. So, thank you for your attention. If you are interested in this study, you can find the full article, which is available. It has been published at the AIVC 2017 conference, and it's available on Airbase.